Okay, welcome everyone. Welcome back to the MISS seminars after a short summer break. I'm pleased to welcome Beatriz Sánchez-Cano, who did a PhD in Madrid before then joining the University of Leicester. Is it like 7 years ago now, Beatriz? I thought I was still there. And recently was awarded a Ernest Rutherford Fellowship from the STFC to continue working on Mars and other planets. And recently, and as of last month, was elected to Miss Council. So welcome, and I'll hand over to you, Beatriz, to give the seminar.
Yeah, thank you so much for the invitation, which came before actually thinking of joining the Miss Council. So I think that was very timely. And yeah, thank you for that. And let me share my screen. Oh. So hopefully you see my presentation now. Okay. So yeah, thank you so much for this invitation, and thank you to all of you to be here today. And yes, today I'm going to talk about mainly Mars, and especially the space weather at Mars, and actually how Mars is considered an unmagnetized planet. And yeah, I would like to use Mars as an example of how the unmagnetized planets behave with respect to the solar wind, even if Mars, as we will see, is a bit special with some kind of small magnetization. So this is the outline of my talk. So I will give first a brief introduction about Mars ionosphere, so just very general aspects for people which may be not familiar with this ionosphere. And then I will talk about the space weather at Mars, but especially focusing on two parts of the system, which are the ones that I have been more involved in the latest year, which is the HF absorption layer. So this is the lower boundary of the system, and also the ionopause formation, which is the upper boundary of the system, which are strongly affected by what happened at the solar wind. And finally, I will conclude with just some closing thoughts. So this is just general comparison, very general about how different planets interact with the solar wind. So we have on the left the typical example for a magnetized planet. I put Earth in here, but this is also applicable to other planets like the giant planets. So you see we have an indirect coupling with the ionosphere because the solar wind directly interacts with the magnetosphere of the planet. And then the global magnetic field from Earth is the one that controls the dynamics that go into the ionosphere. However, for unmagnetized planets like Mars or Venus, so we have another kind of interaction. So in this case, it's a direct interaction with the ionosphere, as we have here on the right. And this is because we don't have a global magnetic field, and then the solar wind drapes about the planet, as you can see in here. And this drape field is the one that is interacting directly with the ionosphere or upper atmosphere of these planets and producing all the dynamics that we will see later. So in fact, this picture is applicable also to Venus and also in a lesser extent to comets, even considering that comets have less, almost no gravity compared to the planets. But there is some particular difference for the Mars case, and are these region in the southern hemisphere, which are so you see a kind of intense magnetization, which are produced by crustal magnetic fields at the surface. So these are the signatures of a former, we believe is a former dynamo that was at the planet, a global dynamo, and this is only just the remnant of that magnetization. But as you can see in here, they interact with the upper, with the solar wind and also with the upper part of the atmosphere. And in particular, so this is a characteristics just for Mars, and these crustal fields, even if they are in the southern hemisphere, they play a big role in the dynamics of the full system, as you can see in these simulations. On a first view, I know that they look like a kind of spaghetti dish, but there are different contributions of magnetic fields. So we have in the middle the planet, we have in blue the crustal magnetic field lines, and then in white we have the magnetic field lines from the solar wind, and then how they drape about the planet. And in different colors we have the different species. I think they are mainly oxygen in here, but yeah, you have different colors. But which is most important is that these crustal fields rotate with the planet. And you see on the left image, so this simulation was taken for 8 UT, and then a few hours after, like if you go to the right on 21 UT, so you see that the configuration is totally different. So this means that even if they are in the southern hemisphere, these crustal fields, so they have the potential to interact with the solar wind, reconnect to the solar wind, and then produce a lot of variability in the ionospheric dynamics that we study. In any case, if we consider the ionosphere, so this is the ionosphere, the formation is really the same for every single body that is near or is near the sun, and also has an atmospheric envelope. So that's why I put in here a generic planet. This is also applicable for bodies outside our solar system if they have a neutral atmosphere and they are relatively close to the star. So basically, we have radiation from the sun that ionize the upper part of the atmosphere on the day side, and also we have particles from the solar wind that have the potential to ionize the atmosphere, especially the lower part of the atmosphere. On the night side, the ionosphere disappears, but sometimes it's maintained through different processes. And these are mainly transport on the night side. And as we will see later, a lot of precipitation of particles from the connection of the tail with the solar wind on the night side. So, which is important to remember is that it doesn't matter the body, but especially for unmagnetized bodies, the ionosphere is really a very important part because it's the layer that connects the atmosphere with space. And so it's the tracer for all the dynamics that we have in the system. So this is really important when we think about atmospheric escape and other processes, because this is the layer that is actually interacting with the solar wind. And in particular, if we focus on Mars, so this is a sketch that I made a few years ago for how the ionosphere of Mars is characterized, or at least what we know of the ionosphere of Mars. So on the left, we have the day-side ionosphere. On the right, we have the night-side ionosphere. So everything that is occurring above this green dashed line is what we actually have observations of that, and everything what is below this layer. So this is mostly theorized because we don't have observation, or mostly perhaps we have only one single observation in some cases. So this is much unknown. But what we know is that we have a layer at 140 kilometers on the day side, which is called the main layer or empty layer. Then we also have a global secondary layer at about 110 kilometers. And this is present through all the day side of Mars. And then we have many sporadic layers. Some of them, they are at the top side, some of them are at the bottom side, and some are created, in fact, by ablation of meteors at the lower atmosphere. And also, we have important to know we have the crustal fields. We believe there is also an electric field affecting the ionosphere. We have a lot of gravity waves because, as you may know, Mars has volcanoes of over 30 kilometers. So imagine the anomaly, the gravity, so it's creating a lot of gravity waves. And also we have some atmospheric cycles like the CO2 cycle that also have an effect on the upper atmosphere. When we move to the night side, as said before, so the main layer disappears because we don't have the sun basically ionizing the ionosphere, but we still have sun ionization, mainly produced by transport and mainly produced by particles that precipitate from the solar wind. As in fact, I will talk later more about this precipitation of particles. Also, there is some important characteristics to consider when studying Mars plasma, and is the variability of the orbit. So you see, like on this left figure, so the Mars distance changed a lot during a Martian year, being the difference between the closest distance and the farthest distance. So it's a third of Earth distance to the sun, so it's really a lot. And this has, of course, an effect on the amount of solar radiation that arrives to Mars. So this is what I'm showing here on the right. So in green, you have the solar cycle variation of EUV flux measured by the time satellite. And in red, we have the same, but extrapolated to the Mars distance. So you clearly see this sinusoidal variation, which is produced by this ellipticity of the orbit. And of course, this has an effect on the ionosphere. And I'm showing in here the total electron content measured by the Mars Express mission for almost also a solar cycle. And in particular, the total electron content, if you are not familiar with that, so it's the amount of electrons that we have in a column of density. And if you remember this sketch of the profile of the ionosphere of Mars, so it's basically the integration of this profile. So it's a very useful number that gives us the amount of ionization that we have. So as you can see in here, so we have the the Martian year with this sinusoidal variation, same as we saw before in the previous slide. And also we can clearly see the solar cycle, because for a period of low solar activity, we have much less ionization than for a period of high solar activity, where we can almost double the amount of ionization that we have at Mars. So this really is a condition for all our studies, because it's not the same to study the system when we are in the low solar activity or at the farthest distance with respect to when we are at the closest distance or at high solar activity. But just even if we have these differences, just this slide is to show, like, actually the ionosphere is the same for any planet or any body, especially if, of course, not considering the large differences with when respect to magnetic field. And this is a nice example of a study that I did last year together with Angeline Burrell when we compare Mars and Earth ionospheres. So I'm not going into all the details of this slide because there is a lot of information here, but in these upper panels, you can clearly see the annual variability of Mars ionosphere, and then on the bottom panel, the annual variability of Earth ionosphere. Of course, at Earth, there is much more ionization than at Mars, but does not imply that the ionospheres are different. And in fact, we found that the photochemical processes in both ionospheres were very similar, especially when non-magnetic field is considered. And for that, we found that a region at Earth where the declination of the magnetic field, it was smaller. It was the period where it was most close, or the region most close to Mars ionosphere. But interestingly, we found that the Martian ionosphere has regions where there were significant transport processes at maximum of solar activity, while at Earth, this happened at minimum. So you see, still there are some differences which are most probably caused by the differences in the magnetic field. Still, the formation and mechanisms and photochemical processes are really the same at both of them. And I think this is my last slide for the introduction. So I think it's also important to show, like, the role of the ionosphere is really important, not only for the dynamics of the ionosphere itself, but also for the full system. And I'm showing in here the bow shock of the planet. So on this sketch on the top, so it's just I'm showing the interaction of Mars with the solar wind. And this black line is the bow shock. So this is the most external boundary of the system. So it's where the solar wind shocks with the plasma of the planet. And on here on this bottom panel, so I'm showing in red the variability of the distance of this bow shock. So if this distance is taken at the terminator, so imagine, so the terminator is this point in here in the sketch. So we took the measurements of this distance of this point, and we evaluated the variability with time. And this is what we have in here. And in green is the same variability without considering the this annual orbital variability in here. And in blue, we have added just the solar irradiance, just to see, like, you can see clearly, like especially the red line follows pretty well this solar irradiance pattern. So this means that of course, the sun has an effect on the bow shock, but also the ionosphere has a role on the formation of this bow shock. Especially if the ionosphere is more robust, because we have more ionization, then it makes that the shock of the planet is found at farther distances. So moving now to actually go on to space weather. So of course, there are many studies that has focused recently, especially since Maven arrived to Mars, on space weather at Mars. But I think this figure on the right summarizes really nice how the full system behaves when we have space weather event at Mars. So this was one of the largest CMEs that we have witnessed at Mars. So it occurred in September 17. You can see on this little simulation on the left, so the sun is in the middle, Mars is here in red, and this big blob in here is the CME that hit Mars. And on the right, there are a lot of panels. I'm not going through all of them, but if you focus on the first panel, so we clearly see the flare. I will remove this. So you clearly see the flare that was recorded by MAVEN. And then after the flare, we have a large solar energetic particle events. So you see in these panels in here in colors. So especially on the E panel, so we have the arrival of electrons, energetic electrons, and on the D panel, the ions. And you see here this gray area shows the arrival of the CME for this period. So you clearly see the enhancement of ions at this time. And also we can see like there were a lot of solar wind protons that penetrate into the atmosphere, as you can see in these upper panels, but they didn't stop in the atmosphere as they typically do. If not, if you go to the bottom panel, so you see these are observations made by the Curiosity rover at the surface of Mars. And you clearly see there is a large enhancement in radiation at the surface. So this has, of course, a lot of, it's very important for when considering that we will send people to Mars in the coming years. So clearly when you have an event of this kind, so there is a lot of radiation that reach the surface. But there is also something quite important in here, is the magnetic topology that we have about the ionosphere, where you can see in here that there are different, each line corresponds to different MAVEN orbits. And we have in blue the times when we find magnetic topology of draped field lines about the planet, in green when we found them open, and in red when we found them closed. So I think this figure, even if there are a lot of panels in here, is really a nice example of all the effects that we have about the planet and also on the ionosphere, as I will show now. So this is another example of space weather at Mars. So these are Aurora observations, and I think these are actually this is a very nice plot. So all of them are real images taken by MAVEN, and on the left we have a kind of aurora which is called discrete, which if you see there are some kind of lines in here, white lines. So these are the auroras that are formed around the crustal magnetic fields, and they're typically formed not typically when we have a space weather event, so but that has been observed several times. But in the middle panel, so we have which is called diffuse aurora. And as you can see, so there is a clear enhancement in the bright of all the pixels in here, but especially at the limb, compared to for example, to the figure on the left. So this is the aurora that is typically formed when we have a space weather event. So it's on the night side, and it's mainly produced by acceleration of electrons and protons. So it's not very clear.
Sorry, sorry.
Some noise. Yeah, it's not very clear if the electrons or protons are.
Beatriz, sorry, on my screen I'm not getting the new figure that you're talking about. It's still got the end little output by the looks of it.
Is now better?
No, I think you're. I don't know if the slides are frozen. Has anyone else got the new?
Maybe I can stop sharing and then share again. That will.
Yeah, try that.
Oh, sorry, I cannot see anymore the, something is happening with my slide, right? Because I cannot see anymore the, how to stop this. So I don't see the controls of Zoom, sorry. Stop video, no, that's my video, right? Oh. Can you see the slide now?
No, it's still the old one. Let me see if I can.
Maybe can you stop
I can stop you.
It seems frozen for me.
Right, there you go. I've stopped sharing for
Okay.
you. Now try resharing and see if that.
I don't see, sorry, I see everything white, so I think I don't see anything. I think it's maybe my Zoom, the one that is having the problem. It's everything like white. I don't see anything. I'm sorry for this.
No worries.
Just wondered,
Yes?
could one idea be to leave? Seems ridiculous to say it, but could one idea be to leave the meeting, Beatriz, and then to rejoin the meeting, perhaps?
Yeah, maybe that will work. Okay, I will try to do that as quick as possible.
No problem.
Okay, sorry, I apologize for this.
No worries.
So on the left is what I said before about the discrete aurora. So you see these lines in here, which corresponds to the signature of the crustal magnetic fields. And then on the middle, so this is the diffuse aurora that is produced. In fact, this is an example for the September 17 event. So you see a clearly global aurora at Mars. So this is produced by acceleration of electrons and protons. So at the moment, I think we didn't get a full idea of which particles are the most important. And then finally, there is a kind of third aurora which occurred on the day side, which is the proton aurora, which is formed as you see on the right by just proton precipitation from the solar wind. So I think this figure is quite a nice example of the different types of aurora that we have at Mars, and especially the middle one, because it gives a lot of information of what happened when we have space weather at Mars. So one aspect that I will show now of space weather at Mars is some issues that we get with radio propagation. And this is a study that this is a topic that I've worked for the last few years. And I would like to show you first the kind of data that I'm going to use. I'm going to show you. So these are, I'm using the Marsis radar from Mars Express. So this is a radar that we have these big antennas at the spacecraft. And there are different operational modes in here, but I'm only using the subsurface mode, in which, in principle, we have reflections from the surface. So this is a radargram on the left that we see in red here, the typical reflection from the surface. And on the right, so I'm also showing the same for other radar that we have on board Mars, Mars Reconnaissance Orbiter, which is called SHARAD, and we get the same. And these are the data that I'm going to use now. So these are basically surface reflections, but as you can see here, the signal crossed twice the ionosphere, which is this region here highlighted in white. And because of that, so typically we get a lot of dispersion of the signals. So from that, we can get a lot of estimates of the ionosphere. But in particular, I will show a case in which the ionosphere totally absorbs the signal. So this is what I have here on this slide. So on the top panels, I'm showing Marsis radargrams, and on the bottom panel, SHARAD radargrams. So on the left, you see the normal ones, so the normal surface reflections. And this changing color means the frequency was changed, so that's why there is a different color. And then on the middle panel, so you can clearly see like we don't have at all a signature of the surface. So these are the cases that I'm going to call they are blackouts, so the radar were blackouts. And as you can see here, there is nothing because the atmosphere basically absorbs all the signals. And there is a third type that I will talk a bit about that, which are the partial blackouts. So, and these are these cases in which you can see the surface of the planet, but it's not as sharp as was for normal orbits like you have on the left. There are also some parts with some absorption, as you can clearly see. So these are what we typically refer as partial blackouts. If you remember this sketch that I showed at the beginning, so this absorption occurs at the lower part of the ionosphere. So this is a region that is typically not ionized, and I highlighted here in the sketch in orange where these layers occur. So in principle, we don't have many observations of this region, but also we don't have ionization. But as you can see, these layers can be very large compared, for example, on the day side with the main layer of the ionosphere. And because they occur very low, so there is a lot of collisions with the neutral atmosphere, and that is why we get the absorption. And the formula is the one that we have at the top. This is a simplified formula because it's much more complex of this. But as you can see, it depends on the absorption, depends on the electron density, on the frequency that we use for sampling the ionosphere, and also on this parameter nu, which is the collision frequency between CO2 and electrons. So in this case, CO2 is the main neutral component of Mars atmosphere. But as you can see, it depends also on the frequency of the radar. So Marsis operates between 1.8 and 5 megahertz. and Sharad operates between 20 megahertz. So as you can imagine, Marsis is going to be much more affected by this attenuation than Sharad. So this is a case for these radar performances, but of course, this is the same for any communications that we try to do with the ionosphere using HF signals. And this is the sample that I was talking before, the September 17 event. So this is how the blackout looks like for this event. So on the first panel, we have the EUV solar flash recording by Maven. On the second and third panel, we have the energetic ions and electrons recorded by Maven. And on the bottom panel, each symbols indicates when both radars were in operation, Marsis for the squares and the circles, and Sharad for the diamonds. And when the symbols are filled, so this means that we lost the signal with the surface, so we had a blackout. So this figure is really nice because it shows for the first time that actually the electrons are the ones producing the blackout, because as you can see, we had at least Mars's blackout for all the time that we have energetic electrons at Mars, but not when we have, for example, in here, there was a lack of ions and we still have the blackouts occurring. Of course, Sharad was blackout less times than Marsis, but this is because the frequency is higher. But still, you see, like for several days, we have this blackout at Sharad. So if I guess you are familiar with this at Earth happening at Earth. So at Earth typically lasts few hours, maybe maximum a day, and they are quite confined. These blackouts are quite confined to the poles of the ionosphere. But however, and here, as you can see, we can have at least 10 days of continuous blackouts in the HF communications, which of course has a lot of implications for future exploration of the planet. And to be fully sure that we were actually considering that the electrons were the source, so we perform a numerical simulation. So this is where we have in here. So we use a numerical model from France, it's called the IPIN model, which I'm typically use a lot for my research. And in there, we simulated the injection of electrons at the top of the ionosphere based on the Maven flux. And what we found, it was this composition for the ionosphere. Again, remember that the main layer of the ionosphere occurred at 140 kilometers. So this is well below the main layer. So we got this electron layer, which is mainly formed by O2+. And then with in a lesser extent, it's also formed by NO+, especially at lower altitude. And when we estimated the attenuation caused by the laser, we got this. So we got for different frequencies, these attenuation profiles. And this is the total attenuation, as you can see at the bottom. And these are the frequencies that we are using with Marsis and Sharad. So basically, this layer could reproduce our observations. And something quite interesting to see is like, in fact, the Aurora intensity profile that was found by the Maven team, it was this one. As you can see here. As you can see, there is a peak at around 60 kilometers in the mission and another peak at around 80 kilometers, depending on which band is used. And this is the same altitude in which we get these absorption layers. So there is really a lot of dynamics going on in here that we really need to understand. And this link with the Aurora is something that we are currently doing at the moment. In fact, we have gone one step forward and not only consider one event, but considering all the events that happens along the lifetime of Mars Express and Mars Reconnaissance Orbiter. And this is what I'm showing in here. So on the first panel is just the sunspot number. On the second panel is the solar irradiance of Mars. And on the third and fourth panel, this is the cumulative sum of blackouts events that we find at Marsis on the third panel and at Sharad on the fourth panel. So these are normalized by the amount of orbit that we have. And also these numbers are considering 6 months of observations. So in red, we have the total blackouts. And as you can see, we have a clear maximum when we have the maximum of solar activity. And but also in blue, I'm showing the partial blackouts, which quite interesting. So we have a lot also during the period of low solar activity, especially for the Marsis radar, which has lower frequencies. So this implies that, of course, for high solar activity periods, we will have more of these HF problems at Mars, but also during low solar activity, maybe we have also some kind of communication problems. So this is quite interesting. Also, we evaluated the location of these events with the planets to see if there was any relation with the crustal fields. And that's what I'm showing here on the top for the day side and on the bottom for the night side. And all of these events, which are color coding here, are normalized by orbit occurrence. And as you can see, there is not a clear relation with respect to the southern hemisphere, which means that when we have an event, it occurs globally and doesn't matter where the spacecraft is or if you are over crustal fields or not. And also, which I think is more important, is if you see the same that we have on the left, but now in a kind of histogram with respect to the solar zenith angle. So you see that, of course, we don't have lower solar zenith angles because the radar cannot operate lower than 50 degrees. But you can see like the maximum, in fact, so the minimum of these blackouts occur near after the terminator, but the maximum occur really deep on the night side where we don't have sun illumination at all. So this really this was really fascinating for us to find. This was totally unexpected. We were expecting more on the day side or near the terminator, but not that on the night side. And this links like possible to the kind of topology that we have, the magnetic topology that we have at the tail. So on the left, this is a really simple schematic of a kind of Venus-like or comet-like induced magnetosphere, where you have draped fields about the planet. Of course, this is really, really simple, but this is like the general picture that we have. But on Mars, with the crustal fields, so this is really much more complex. And this means that we have drapes perhaps on the day side, but on the night side, we have all this twisted and complex topology where we have in blue the closed field lines, in yellow the draped field lines, and in magenta we have the open field lines. So all these lines, we believe, they're contributing to the creating of the aurora on the night side of Mars, but also to the creating of these global blackouts that we have on the night side of Mars, even when in principle we should have less ionosphere. So this is an ongoing study, this comparison with the topology and the blackouts, so really stay tuned for that, because in fact, I'm really excited of this study that we are doing at the moment. So moving that's the last part of my presentation. So moving to the upper part of the ionosphere. So I said at the introduction that also the boundaries were very affected by space weather. And in fact, there is something which is like a full mystery on Mars, and this is the ionopause formation. So if you are not familiar, so these are quite nice plots taken by the Venus Pioneer orbiter in the 80s and 90s at Venus. So this is the formation of the ionopause, which is the boundary that separates the cold plasma of the ionosphere from the hot plasma that came from the solar wind. So on the left, this is a classical example that appears in all the books because it's really nice. So we have in black the magnetic field at the top of the ionosphere, and then in orange, I highlighted the electron density from the ionosphere. So you see like there is a balance between the magnetic field that came from the solar wind with the thermal pressure, in this case, electron density from the ionosphere. If the magnetic field is larger because there is more from the solar wind, so then the ionosphere is found at lower, the ionopause is found at lower altitude, and this means that the ionosphere is also more compressed. And there is like a clear boundary, as you can see here, is really the end of the ionosphere. And this last plot is the scale is for the magnetic field is different. Just take that into account. So you can clearly see that we have a larger magnetic field, and then the ionopause goes deeper, and also the magnetic field. So the ionosphere became magnetized, as you can see here with this profile. And on the right, I'm showing another nice example. So because this pressure balance is pretty nice. So the electron temperature is actually a nice parameter for identify this ionopause. And as you can see, for example, in pinking here, so we have a small rise in the electron density, in the electron temperature at this altitude. And if you go to the left, so this is where the ionopause is found. So if you focus on the blue, it's the same. So basically, when you have this rise in the electron temperature is when you have the decrease in the density, and indicates the ionopause. Of course, this is because the plasma above the ionopause is hot. So that's why you have this rise. However, at Mars, this is like a full mystery. So there has been a lot of studies trying to identify the ionopause, but the ionopause is not always present. So sometimes some authors has has said that the ionopause is only formed 9% of the cases. Others, it's formed about 50% of the cases. So it's really not clear. So what we have done, it was to take some MAVEN observations and try to get more insights of this pressure balance and why this happens or not happens at Mars. So following the previous slide, the case of Venus, so this is our methodology here showing on the right. So basically, we took electron density profiles in blue and electron temperature profiles in pink in here. And when we saw this rise in the electron temperature, then we went to check if we had a decrease in the electron density. And if was that the case, then we identified the ionopause. But as you can see, most of the cases we have the bottom configuration where there is not a rise at all in the temperature and there is not a decrease in the electron density. So this is really like a really mystery at Mars. So we took all these profiles with and without ionopause, and also we separated them from the regions when we have crustal fields and where they were over the crustal fields. And what I did was to estimate the total magnetic pressure and the total thermal pressure, which is what we have in here in these plots. So in red, we have the magnetic pressure, and in green, the thermal pressure. And as you can see, starting on the left, so these are profiles far from crustal fields. So the first thing that you can see clearly is like the ionosphere is magnetized all the time, which is quite surprisingly. And this is not the case at Venus at all. At Venus, is only in few particular cases when the solar wind when there is an space weather event, basically. And this balance that at Venus occurred at the ionopause, so in this case, the balance between the thermal and magnetic pressure really occurs really low in the ionosphere, really very close to the peak of the ionosphere. So this is like a first difference with respect to Venus. And the second difference is that sometimes we have ionopause, as we see on the left, and sometimes we don't have ionopause, and you see on the right. And the system behaves practically the same for both cases. When we compare what happened over crustal fields, we still see the same profile, the same signatures. Some of them with with ionopause, and some of them without ionopause. Although it's true that there is much less ionopause formed over crustal fields than far from crustal fields. So this implies that something is happening with the solar wind. So what we did then, it was to try to compare with the dynamic pressure from the solar wind, but unfortunately for this data that I'm showing in here, we didn't have solar wind dynamic pressure from the solar wind from MAVEN, and we only had solar wind density, which of course is not the same that the dynamic pressure, but unfortunately we didn't have the velocity to estimate the pressure itself. So that's why I'm not plotting that on the same plot, but I'm showing here in blue just the protons of solar wind protons measured by MAVEN as a proxy of dynamic pressure, or at least as a proxy of indicating the presence of solar wind at the region where we have the ionopause. And as you can see here on the left, where we have this dashed line, which indicates the ionopause altitude, is where these solar wind protons basically stop. And on the right, when we don't have the ionopause, then we don't have this increase in solar wind protons. So we just have the normal amount that we will find, for example, here at lower part of the ionosphere. So there is really, for the formation of the ionopause, there is really a lot going on with the dynamic pressure. And what we did, it was to compare with Mars Express observations, that Mars Express it was on the solar wind at this time, and we could get some estimations. But of course, the statistics are not that good as with MAVEN, and this is because we only get single observations from Mars Express. And this is what I'm showing in here. So in dark blue, we have for 3 different periods of time. In dark blue, we have the solar wind measured by Mars Express in the solar wind. In light blue, we have the kind of magnetosheet dynamic pressure that we can get, but only at the magnetosheet. So it's really not at the ionosphere, and it's really not at the solar wind. So it's a proxy for. And in pink, I'm showing the total pressure at the ionopause, which is the thermal plus magnetic pressure that we find at the ionopause altitude. And as you can see, so in general, so there is a nice agreement between these 3 pressures in these plots. Of course, there are some differences, but this is because the spacecraft were at different places over the planet and watching slightly different conditions of the solar wind. But in general, the agreement is pretty well. So what we can conclude is like when there is an ionopause, it's really a balance between the upstream solar wind dynamic pressure and which is the pressure outside the system and the pressure inside the system in the ionosphere. And these rises that we see in here, they correspond to, in fact, to a space weather event. So mainly we have ionopause when we have kind of a space weather activity at Mars. And this is, I think this is my my last slide of the science. So this is a comparison of this pressures balance at Venus and Mars. On the left, we have the dynamic pressure on the y-axis and the total pressure on the ionopause on the x-axis. And you can clearly see at Venus this nice one-to-one trend. At Mars, we have the same on the right, and it's not that obvious, but if you see the data are more, first the pressure is lower than at Venus, and the data is more scattered than at Venus, but still the red line is the median pressure per beam that we did for this comparison, and it's almost one-to-one as well. So it's really, when we have the ionopause, it's really the same as Venus, but the problem is like this is only few times in few orbits basically, because most of the time, so there is not a balance between the solar wind pressure and the ionosphere that is not able to create this ionopause. So just to conclude, that's glad to say, like there is a lot of things to do at Mars, but there is something that we are at the moment lacking, and is we don't have, like at Earth, we don't have a satellite just acting as a solar wind monitor for Mars. So this means like if Mars's place is stopped, it's not extending beyond 2022, which may happen. I hope not, but may happen. So we will have a serious problem with our plasma observations, because we won't have any more solar wind monitor at Mars, even if Mars's place is not ideal, because of course it's moving around the planet. It's not always in the solar wind. It's now doing that. But at the moment, we don't have any other spacecraft do that. So we really are going to have some problems if we don't get to do that. And finally, I think this is really the future that we should have at Mars. So this is like the dream, kind of big constellation of satellites that will give us insight of all the dynamics that you can see here on the left. So my presentation only focused on very tiny aspect of space weather, but as you can see here on the left, there are tons and tons of dynamics and different things that happen at the system that we really don't know. And I think we believe only with kind of constellation as this movie on the right, it will be possible to have that. So of course, this is a dream, but at least NASA made a nice study last year about this kind of constellations in particular, but we really hope both all the space agencies really take this into consideration, because this is the really next step for this kind of science. So just to conclude, I hope you at least can get some general ideas from this presentation. And if there is something that I would like to highlight is this question first, is really Mars an unmagnetized planet? Okay, it's true that there is not a global intrinsic magnetic field, but we have crustal fields that really are really important for plasma dynamics. And also we find that the ionosphere is mostly magnetized all the time. So I'm not sure anymore if this question that everyone assumes Mars is unmagnetized is really true. Also, the space weather is really intense on Mars, and this is because we don't have the global magnetosphere. And we know that this is already causing a lot of significant effects on HF propagation. Of course, this has a lot of implications for human exploration, but also for robotic exploration, as we are sending more rovers at the surface of Mars. And I think something important to get is like we still don't have a good characterization of the most upper part of the ionosphere. And this is a region important for understanding everything that came into the system. So this is really where the solar wind dynamics start to play a role in the ionosphere. So there is still much more work that we need to do in this region. And of course, there is an absolutely need for these coordinated multi-spacecraft observations to at least answer these two main points about the space weather that I talked today. So thank you so much for being today. And I'm really sorry for all the technical problems that I had. So hope you enjoy and get something about Mars today.
Thanks, Beatriz. I thought it was an excellent talk. Has anyone got any questions? So either raise your hand or drop them in the chat.
maybe I will. I have here. I was thinking to stop sharing, but maybe no. I can see you now here.
Well, wait, I've got a quick question about the sort of the implication of the space weather on human and further exploration of Mars. So that does seem to pose a real problem, right? Having 10 days of radio downtime, for example. Is there any ways that could be mitigated, or is there like it looks like you're going to have to use a lot more planning, right? In those sort of missions. Is that something that's being looked at?
Yeah, well, it's something that we are at the moment investigating. I think there is no possibility for mitigating this. The only mitigation could be to use perhaps higher frequencies. But the problem is we are not sure which is the limit for these HF problems. So we need to understand if, for example, the rovers also suffer, because the rovers use ultra high frequency. So we need to understand if these frequencies are also affected when we have these kind of events. So this implied a lot of work, and also these data are typically not available for public. So it really implies a lot of planning with the agencies, if they want to, and they are happy to give you the information about the relay communications and this kind of thing. So there is a lot of going on in here, but I think it's something that we really need to characterize for the future, not only for humans, but also for robotic exploration, because as you said, if we have a big space weather event, like the Halloween event or something like that, then we are totally solved. So we can even have problems with our, with the instruments and everything, because a lot of radiation reaches the surface, and so this is something to characterize.
Yeah, that was going to be a follow-up question actually. Was sort of if you've got astronauts on the surface and there is a large event, are they at quite a lot of risk for sort of that like radiation dosing?
Yeah, I don't have, on the top of my mind, I don't have the doses that they get, but there has been a recent study by there is an instrument on board the Curiosity rover, which is called the radiation instrument, the RAD instrument. And I think they have published recently a very nice overview of the radiation doses that you can get at the surface based on, but first based on the trip to Mars, and then based on when you have a solar storm, the amount of level of particles reaching the surface. But it's really, at least for the September 17 event, it was a large event. So maybe I can go back to the slide of the general overview of the event. Sorry, this one. If you can see here, so the bottom panel is the rover Curiosity. So you clearly see the enhancement in the radiation, the particles reaching the surface for several days. So it's really a lot of problems and a lot of things to think if humans are being sent to Mars and how to shield them, and which also give, sorry for talking a lot, but if we will have a Sentinel spacecraft in the solar wind, it will also help humans to look for shelter. But at the moment, if we lose that, so it's really like a risk. So
yeah, you've got to rely on modeling, right? We've got a couple of questions in the chat. So Steve Milan's asked, why do the radars use the particular frequencies they do, e.g. the HF as opposed to higher frequencies?
Yeah, so they use that because let me show you the radiograms. So this is because these frequencies are especially designed to sample the subsurface of the planet. So if you see on the left, so this is Martian. So these lower frequencies are really affected by the ionosphere, but at the same time they can penetrate deeper into the system. I know it's hard to see, but if we do a zoom in the signal, you clearly see a lot of layers in the subsurface. Perhaps this slide is better. So you clearly see a lot of things in here. And then Sharat use a higher frequency, which have better resolution, so it's less affected by the ionosphere, but the penetration is much lower. So you only get very shallow altitudes of deepness in here. So each frequency is designed for that. So that's why. So they have also some effects on the ionosphere, but otherwise, if you want to sample the subsurface of the planet, you need to use these frequencies.
There's another question about whether is there any association between the radio blackouts and the neutral atmosphere weather events, like e.g. Gravity wave coupling?
So I think this is because this is quite new for us. So we knew that these blackouts occurred, but the reason until we did this study, it was not started to get understood why this happened and which particles were producing this. So this is really new. This is true that we need to investigate also what happened with the neutral atmosphere, and I think that at Earth this also is an important role and plays a role. But on Mars, this is really relatively new. So I think we really need to. There is a lot of things that we need to do basically, and it will be really nice to have more people also working on this, because I think this is really important, and there is really a lot of things important to consider. And I absolutely think they will have an effect, because gravity waves and neutral winds already have a strong effect on Mars ionosphere. And I fully believe this will also have an effect on blackouts. But at the moment, we don't know, because I think we really need more studies on this.
And I've got two follow-up questions two questions from Andrew Coates. So the first one was that you mentioned Mars's ionosphere is usually magnetized. Is that only near the crustal fields, or is that away from them as well?
So we have found that this is everywhere on the planet. So let me show you again this figure. Maybe I was too fast in here. So on the left, so we have profiles that were taken far from crustal fields. So they are mainly from the northern hemisphere, and on the right is just over the crustal fields. And as you can see, the red profile is the magnetic pressure. So it's basically everywhere. So it's true that in some cases, when a high solar activity, maybe we will find that there is not magnetization in the ionosphere. But at least for the time that MAVEN has been at Mars, this is what we have always found. So there is really always magnetic field, even if perhaps it's not too strong, but there is always magnetic field even far from the crustal fields. This is quite interesting, I have to say. And I think the main reason is because the thermal pressure is quite low compared, for example, to Venus. So that's why the magnetic field is easier for the magnetic field to enter or be induced in the ionosphere.
And his second question was, how do the new UAE HOPE Aurora images compare to the MAVEN ones, if you've seen them?
For the Auroras, you mean, or for?
Yeah.
Well, I think during the NAM meeting, so the HOPE team show very nice plots and about the auroras like this one. So they were focusing on the discrete aurora, because I think this is what they observed, and I think the quality was really good. I was really pleased to see those images. So I'm sure they will do some kind of cross calibration between MAVEN and the HOPE mission for comparing this. But I think with two spacecraft measuring this aurora, they're going to give us a lot of information also, especially spatial and temporal resolution of the formation of these processes, which in turn they occur in the ionosphere also. So there's everything in the end is linked. So yeah, I don't know at the moment, but they look really nice. I'm really looking for that.
That's cool. And probably one last question that's in the chat before we end. During the blackouts, can you see an induced magnetic field on the ground?
Yeah, well, that's other nice question. So yeah, honestly, I don't know. I didn't have a look. And at the moment, there are two magnetometers at the surface. So there is one by the InSight mission and another one by the Chinese mission. I think the Chinese mission, the data are not available, but the InSight mission, so there is a problem. I believe there is a problem with the magnetometer, because the magnetometer, so the spacecraft is not magnetically clean, so they need to do a lot of processing. So that's why I didn't ask the team to look for those data yet. But of course, this is something that we should do, because especially once we have a relatively large space weather event, so we can have like a full picture with MAVEN, Mars Express, and then Sharat, and then the surface with InSight at least. So yeah, you see a lot of things to do still. I'm really how to say, I'm really happy for everything. It's like more work to do, but it's like everything is coming together. So, but yeah, definitely something to look at are the magnetometer.
That last question was from Heather McGreedy, so I didn't. Yeah. Okay, right. Well, I think unless there's anyone else got another quick question, I think we should thank Beatriz again for a great seminar. You can use the little reactions and give a clap. And yeah, and look out for the October seminar that will be coming up next month. Thanks everyone, and have a good lunch and enjoy possibly the last bits of summer, as it's nice and sunny here in London. Right, thanks everyone.
Bye bye.